Welcome to lesson 2 from week 1, and this is where we're going to review your physics test. So we're going to go through the answers. So you need your copy of your physics test, which obviously you need to have completed. You need a colourful pen, preferably colourful, so that when you write onto your answers, so correct them or mark them wrong or whatever you're doing, it shows up well. And I'd also recommend that you have a copy of the mark scheme as well, which you can find on Shobi, because for each question, I'm going to go through the best answer, but there might be some other options. So what you're going to want to do is pause it after I've answered it and just check if you haven't written exactly the same as me. Check if there's other possible answers on the mark scheme, okay? Question 1. The bar chart below shows the energy resources used by a country. So there's the percentage of energy, and then there's the energy sources: coal, gas, nuclear, oil, solar, tidal and wind. Question A. State the name of one of the renewable energy resources shown in the bar chart. And it's really important you don't make one up, you use one that's here. So we're looking for renewable energy resources. So solar is, tidal is, wind is. So in your answers, you could have had solar, tidal, or wind. You don't need all three, you just need one for the mark. If you get the mark, I recommend that you circle it like that each time, because it makes it much easier for adding things up later. Okay, question BI. State the names of the 3 fossil fuels shown in the bar chart. So again, I'm going to go up here. I don't want to use the same colour, so I'm going to circle it in my pink pen. So wasn't concentrating there, so I'm going to circle them in my pink pen. That's why I always use an erasable pen, boys. And I have, of course, got coal, gas, and oil. So you don't need to say like crude oil or natural gas or methane or anything. You just use the names that they've given you. And that is an easy 3 marks there, guys. Okay, use information from the bar chart to calculate the total percentage of energy supplied by the fossil fuels. So you're calculating a percentage here, so you need to be using your maths skills. So first of all, we need to look at the graph and work out. So we've got 30 plus, so if this is 10, I'm actually going to mark on the graph to make sure I don't make any mistakes. So every 5 squares is 10, which means that that's worth 2, 4, and it's halfway between, so that's 25. And then oil is on the 10 line, plus 10. Okay, so 30, and you can do this on a calculator, remember, but 30 and 10 is obviously 40, 50, 60, 65. And it's already in percentages, so that is 65%. So you get 1 mark for the 65, and you get 1 mark for the workings. So 1 mark is for showing your workings, remember, guys. Okay, on to question C. State one advantage and one disadvantage of using fossil fuels as energy resources. So there are multiple possible answers here, boys, so you will need to check the mark scheme. But I'm just going to give you one for each, obviously. So when you use a fossil fuel, you produce a large amount of energy. And another really obvious one is it's really reliable, because you've got a reliable source of coal or oil or gas. A disadvantage is obviously that they are running out, they are non-renewable. So that's a really obvious one. Another obvious one is that it produces pollution. And the more you can show off your knowledge, the better, really. So if you're saying produces pollution, why not go ahead and mention CO2 if you have space, just to really show off your knowledge, guys. Okay, so that's 2 marks for that one. So I've turned over to the next page, and here we have a diagram. It says the picture below shows how waves can be used to generate electricity. So this is the renewable energy made from waves. Number the boxes below 2 to 5 to indicate the correct order in which electricity is generated from the waves. So this is all about getting the correct order then, guys. So let's have a look. They've done number 1 for us. So number 1, a wave causes water to move up the air chamber. So here we go. Here's the wave, here's the air chamber, and what they're saying is that the water is being moved up there. So I like to draw onto diagrams to really help myself understand what's happening. So when it moves up there, what's probably going to be happening next? So air is going to be pushed out of the chamber, obviously, because if you've got water pushing up, it's going to push the air out. So if you look, the only way it can come out is up here where the turbine is, which means that the air is going to turn the turbine, and then the turbine is linked to the generator. So the turbine is going to turn the generator, and the generator is what produces electricity. So our order is 2, 5, 1, 3, 4. And with that, you only get 3 marks if you get all of them correct. If you have, you get 2 marks for any 3 in the correct order, and that includes number 1, even though you didn't have to do it, and 1 mark for any 2 in the correct order, and that includes 1. Okay, so B. These might seem a bit funny, guys, because we've gone back to A, and that's because I've kind of cropped lots of different questions together in this test from lots of different papers, so don't worry too much about that. All right, name the form of energy transferred to the turning turbine. So the energy that's been transferred to the turning turbine. So anything that is turning or moving is movement energy, which, if you remember, the proper name for movement energy is kinetic energy. You don't need the word energy for the mark, you just need the word kinetic. Oops. Okay, state one advantage of using wave energy rather than fossil fuels to produce electricity. So why is it an advantage to use waves? So it's really the obvious answer here, guys. It's renewable. Waves aren't going to run out. They're caused by the wind, and the wind is caused by the sun. So they're never going to run out. They're renewable. The other obvious one is that it doesn't cause pollution, or doesn't cause polluting gases, like CO2 and SO2 and NO2. Okay, and let's go on to the rest of the question. Another way to generate electricity is to use a wind turbine to harness the energy of the wind. The picture below is of a small wind turbine, and the graph shows how much electrical energy is produced at different wind speeds. So if we look at the graph, there's the energy output, so essentially how much energy is being produced in kilojoules, so 1, 2, 3, 4, 5, 6 kilojoules, and then the speed of the wind in meters per second. So, for example, if the wind is only 2 meters, you're actually not going to produce any electrical energy. Whereas if you've got 10, is that meters per second, I think, by the look of it? If you've got 10 meters per second wind, then you're getting, looks like 5.5 kilojoules of energy per second. All right, so the energy output is given in kJs. State what the J stands for in the kJs. So J, they're asking what energy is measured in, and it's, of course, joules. That's my boiler making lots of noise. Be quiet, boiler. Okay, we're just going to have to go on in the face of adversity, guys. So, suggest why no energy is generated when the wind speed is less than 2 meters per second. So this is a question where you're not going to have been told or taught this answer. You need to kind of work it out, use your brain, do some scientific thinking. And if we look at this turbine, you think this is quite a big, heavy piece of machinery. Think about what would need to happen for it to move. Well, you need quite a large energy input to actually get it moving, get it spinning around. So it's simply that this amount of energy is not producing a big enough force. So the force of the wind isn't big enough to turn the turbine. Now, in the mark scheme, they mention the fact that that's because the frictional force of the turbine is bigger than the force of the wind. I don't think you need that level of detail, guys, but if you do mention frictional force, that's excellent. Well done. Okay, I think this is the last part of this question. Using the graph, and again, I always like to highlight that because often people ignore the graph even when they've been told to use it. So using the graph, describe how the energy output varies with wind speed when it is more than 2 meters per second. So that's quite a complicated question, actually. So let's have a look at the graph. So if we look at this graph, it isn't a straight line, it's a curve, isn't it? So that's a really important feature. And if we look back at the question, it's worth 2 marks. And if it was a straight line, it would only be worth 1 mark because we'd only be able to make 1 point. So if we look at this part of the line, in fact, let's split it kind of, yeah, I'm going to split it here, but this isn't an exact thing. If we look at this stretch here, it is increasing, but it's increasing quite slowly between 2 and 6, isn't it? Once we get to 6, it's actually starting to increase a lot more. And if you look at the very last stretch here, that's a really, really rapid increase, isn't it? So what I probably wanted to do is kind of divide it into 2 parts that I'm going to talk about. I'm going to talk about the first part where as the wind speed increases, the energy output increases slowly. And then after, I'm going to talk about how it increases at a rapid pace. So, all right, so my first bullet point, I'm going to put up to 6 meters per second wind speed. There is a slow increase in energy output. And then because I've put up to, I'm going to put after 6 meters per second wind speed. Sorry about this background noise, guys. I can't do anything about it. There is a rapid increase in energy output. So I really like to use this kind of standard approach of these 2 sentences are essentially the same. The only difference is I've put up to and after, and here I've put slow and here I've put rapid. So I'm really keeping to a format where what I've done is I've linked the input variable to the output variable, or independent variable to the dependent variable. I've linked those 2 together using comparative language, and I've done that both times. So that would definitely get me my 2 marks. Now there are other things that you could write if you look at the mark scheme. You don't have to have written this. But don't give yourself a mark unless you've made a valid point, and certainly don't give yourself 2 marks unless you've made 2 valid points. Okay, guys? And that's the end of this question. In your mark scheme, I think there is a part G, but we haven't got that on here. So that's the end of this question. So add up your marks, and on the front of your physics paper, if you record how many you got out of 17. So for example, I got 17, obviously. So you can record, actually it's better to do it in your colour, record how many you got. Okay, question 2. Complete the following energy transformations. So you just have to fill in the missing words. You don't have a list of them, but they should be fairly easy. So a Bunsen burner transforms chemical energy. That chemical energy is in the methane gas, and it's changing it into what type of energy? So you've got 2 different options here. You've got thermal energy, which is the useful energy. So really that's the one you should be going for. The other, of course, is light, but that's not the purpose of a Bunsen burner. So try and use the one that is the useful energy, but I would allow light. Okay, when plucked, a guitar string transforms what energy into what energy? So when you pluck it, it obviously moves. So that is kinetic energy, and it's obviously being transferred, because it's a musical instrument, into sound energy. There are other options here once again, so check the mark scheme. Okay, a falling apple transforms what energy into something energy into something energy? So there's 3 energies here. So the apple starts off with gravitational energy because it's obviously up high in the tree. As it's falling, it's got kinetic energy. And when it hits the ground, it's going to produce thermal energy as it hits, because anything, if you hit your hands hard together, you'll feel like heat being produced. However, it's also obviously going to produce sound, so I would allow sound energy as well. So 1 mark for the first one. Obviously you get 1 mark for each correct one here and 1 mark for each correct one here. All right, moving on. The law of conservation of energy, which we did do, remember, states that energy cannot be created or destroyed. It can only be transformed from one form into another form. Using the example of the falling apple, explain how the law of conservation of energy applies to that energy transformation. So we've basically got to explain. So our command word is explain, not describe. So explain how this is linked to the law of conservation of energy. Okay, so all of the gravitational energy the apple has is transferred. Oh, they've used transformed, so let's use transformed. Is transformed into kinetic. So I'm just going to tick that I'm using my keywords. Kinetic energy as the apple falls. All right, so my first bullet point, because remember we always use bullet points when it's worth a few marks. My first bullet point, I'm going to be giving myself a mark for talking about the gravitational energy being transformed, and I'm giving myself a mark for saying that it's been transformed into kinetic energy. Then my next point, I want to say all of the kinetic energy is then transformed into. Now, I'm going to list thermal and sound, but you don't need to actually mention both as long as you say that it's transformed into another type of energy, and sound energy. All right, so again, I've used my keywords. I've got lots of keywords, in fact, in here. So I've got gravitational, kinetic, transformed, thermal, sound. I've got all of those. Now, it does say 1 mark will be awarded for correct spelling, punctuation and grammar. I'm not too worried about that, actually, guys. I would like you to have used bullet points, ideally. But what I'm more worried about is that you've got the keywords in there. And that obviously your sentences make sense. So award yourself a mark. You do need to have said all. That's really crucial, that all of the energy is being transformed. So if you used a word like all to mean all, that's fine. So it's really crucial that you said all of this energy has been transferred into another type, and all of this energy is then being transferred into that next type, okay? So always, I would say, if you don't think you've quite said it, don't give yourself the mark, because science teachers aren't going to be generous with you at your next schools. They're not going to be like, oh, I know what they meant. So it's only really on what you've written, not what you meant to write. Okay, guys? All right, so moving on to the next part of the question. So Samya is a skydiver. She is practicing her landings by jumping from a 4-meter high platform. She is attached to straps which act like her parachute. So this is kind of like a parachute setup. So A is her standing on the platform. B is halfway down. And C is on the ground. So we actually need to turn over for the next part of the question, but obviously we're going to need to refer back to this diagram. Okay, so look at the statements below about Samya's energy as she practices her landings. Put a tick in the correct column to show whether each statement is true or false. So you're going to put a tick only. You don't need a cross, just a tick in anything that you think is true. So let's start. At A, all of Samya's energy is gravitational potential energy. So make sure you're referring back to the diagram. So is it all gravitational potential? So yes, it is, because she's standing up on that platform. So we have a tick there. So then the next one, between A and B, so between A and B, Samya gains gravitational energy and kinetic energy. Well, she is going to gain kinetic energy because that's when she's jumped off, if we look. So she's just jumped off at A and she's falling to B. So she's moving at that point. But she's not going to have any more gravitational. In fact, she's losing gravitational as she falls. Obviously, the higher you are, the more gravitational, and she's going downwards. So no, that's false. So we're going to put a tick, remember, in the false column. All right, between A and B, so the same position, Samya gains only kinetic energy. Yes, because she's falling at that point, as we said when we just looked there, so that's true. On the ground, Samya has 0 kinetic energy. So when she is at C on the ground, she's got no kinetic energy. Well, she'll have landed, so she won't be moving, so absolutely that's true. And then the last one, on the ground, Samya has her maximum gravitational potential energy. Well, no, because she's not up high. So remember, the higher we go up, the more gravitational. So that one is false. So it's worth 4 marks. You need to get all 5 to get 4 marks. If you get 3 or 4 answers correct, you get 3 marks. If you get 2 correct, you get 2 marks, and 1 correct, you get 1 mark. And that's the end of question 2. So add up your marks and go to the front. Go to the front of your paper and write in how many you got. It's out of 13. All right, so question 3, there actually weren't hardly any questions on this part of energy, so the heat part. the thermal energy part. So actually I had to make up some questions here, guys, which does tell you that it's not something that comes up in exams a lot. So you do want to focus your revision in other areas in future. Right, so the diagram below shows a thermometer, obviously. Estimate the values shown by X and Y. So unlike a normal thermometer, there's no scale on here, so we're going to need to estimate. They do, however, tell us that this is 100. Now, what I would have done is I would have got my ruler and I would have measured from 0 to 100. So annoyingly, it's 95 millimeters rather than 100 millimeters, which is very irritating. I'm guessing that is because I slightly changed the size of things, guys. So that's going to mean that about 47.5, that's going to be 50 degrees. And then our X is here. I'm just going to mark those onto here. So it's really important that you use a ruler to do this, everybody. I'm going to allow you maybe a bigger margin for error just because I think the size of this should have been so that it's exactly 100, but because I copy and pasted it, it must have resized itself. So if this is 50 here, this is exactly halfway between 50 and 100 if we look. So that's obviously meant to be 75 degrees C, but I'll allow you, let's say you got 5 either side of that. So if you put 70 or 80, anything either side of that, that's fine. And then here, if we look, that's, I would say 10 below. So I'm going to put that as 40. But again, let's give ourselves a leeway of 5. So if you had 45 or 35, anything between those, that's going to be fine, guys. All right. So the key thing here is that you actually bother to use a ruler to write your answers, to work out your answers, to do your estimating. Okay. And you get a mark for each of those. All right, then I, as I said, made up some questions. So explain how a thermometer works when you put it in some hot water. So let's use bullet points for this, and let's think about what keywords that we need to use. So on a thermometer, we have alcohol in here, and we should have up here a scale that we read, and it works because the alcohol expands as it's heated. So let's try and use those 3 keywords. So as the alcohol gets hotter, because we said it was in hot water, it expands. So there we go. I've used 2 keywords in this. This causes the alcohol, try to avoid the word it, be really specific about what you're talking about, to rise up the scale. And then my 3rd bullet point, just to really make sure that I've got the marks, then you can read the temperature off the scale. There we go. So really I would give the marks for expands and rising up the scale. That's where we're looking for marks. So if you didn't use the word expand and you didn't use the word scale, you can't give yourself the marks, I'm afraid, guys. Okay, and then the last question for question 3, what is the difference between a conductor and an insulator? So again, I'm going to use bullet points, and I'm going to start with talking about a conductor. So a conductor, and because this is about thermal energy rather than electricity, I'm not going to bother mentioning electricity. So a conductor lets thermal energy, you can say heat, that's fine, pass easily through. And then I need to talk about an insulator. And because it's a comparison, I'm going to use the word whereas. Whereas an insulator. You can just say does not. But I'm just going to really make sure by saying doesn't let thermal energy pass through. And we do need the word easily because it will eventually let thermal energy pass through. So it is quite important that you put that word easily in there. Okay, so that is the end of question 3. So add up your marks. And then go to your front page. Give yourself a mark out of 6. Okay, question 4. Jonathan has a model boat with an electric motor to drive its propeller. 2 of the forces that are acting on the boat as it moves across the school pond are shown in the diagram below. So it's got thrust and weight. So I would highlight those on the diagram to make sure I don't forget about them. So A, state another horizontal force on the boat. So of course horizontal is this direction. So we've got thrust. So what's going to be working in the opposite direction to thrust? That's what you should be asking yourself. So the opposite direction to thrust, well, there's 2 potential. There's water resistance from the water in the pond, and there's also going to be air resistance. Remember, the other name for air resistance is drag. Either is fine. Okay, and then vertical. So that's this plane here. So weight is what's pulling our boat downwards. So what's going to be working in the opposite direction to the weight? Well, because it's in water, it is, of course, up thrust. So if we think in the air, it is thrust. In water, it's up thrust. And on a solid, it would be reaction or support force. So up thrust is the only possible answer there. All right, draw labelled arrows on the diagram above to show the 2 forces in A. So I actually already drew them earlier, so I just need to label them. So I'm going to label this as up thrust, and I'm going to label this as water resistance. Now, they haven't told us anything about the size of any of the forces acting against at the moment, so it doesn't matter too much what size arrow you do, but of course you should be drawing these in pencil. I've drawn them in an erasable pen, so that's fine. But if you're drawing onto a diagram, it should be in pencil so that you can rub it out if you need to. All right, so that's us with the drawing part. So now we're going to look at this bit here. The speed of the boat is increasing. Okay, so that tells us that the thrust of 25 newtons, that is a large force. It then says, suggest values for the 2 forces that you have named in A. So if the thrust is 25 newtons, that means that the water resistance and air resistance must be less than 25 newtons. And that's them combined. So I would probably go for something quite small for the water resistance. So let's say that combined they add up to 20 newtons. So then let's say that I would maybe guess at 10 newtons for the water resistance. But anything less than 25 is acceptable. But ideally a nice small number there, guys. Okay, and then the vertical force, so the up thrust, they've asked for as well. Well, if the weight is 20 newtons, that tells us that the upthrust must also be 20 newtons. If it was less than that, then our boat would be sinking, which obviously it isn't. And if it was more than that, then our boat would be thrust up into the air. Sorry for the little tapping sounds. That's Dougie coming to say hello. Hello, Dougie. Hello. So 20 newtons is the only viable answer for that. Okay, and then the last part of the question. The propeller continues to produce a thrust of 25 newtons, and after a few minutes, the boat reaches a steady speed. Explain in terms of the forces why the boat has reached a steady speed. So if it's going at a steady speed, that immediately tells us something about the forces. It tells us that they must be balanced. The other key word that you can use that means balanced is equilibrium. Either is fine. So I always, again, write myself these little notes to work out what's happening. So let's start with our first bullet point. The air and water resistance must have increased to become equal to the thrust. Therefore, a steady speed is reached. So again, you don't need to have this exact wording, but what you do need to say is that so I've used the word equal, another word that means balanced. So you do need one of these words. That's one mark, certainly, that you're looking for. So one of the mark is for saying that it's equal or balanced. The other mark is there's a few different options. So it might be for saying that the air resistance and water resistance increased. That would definitely be worth a mark. It might be, there are other options on the mark scheme talking about that there's no resultant force. So that's a mathematical term that you might remember from the topic. So have a look at this answer, have a look at the mark scheme, compare it to yours. Remember, once again, you need to have made 2 separate points to get 2 marks, okay? So add up your marks and put them here. Question 5. Some pupils decide to measure the speeds at which they travel down a slide in the playground. They measure the distance from the top to the bottom of the slide as 5 meters. So it's shown on here, 5 meters. So again, I'd always highlight my diagram. Amy's time down the slide is measured 3 times, and the times are shown in the table below. Here we go. Complete the table by calculating the mean time taken by Amy to slide down the slide. So they're just asking you for the average. The fact that you've got a space here, if you look, they've got a space and then the mark, that tells you they want to see workings. So 2.7 plus 3.1 plus 3.2. And again, you don't need to do this in your head, guys. You can use a calculator. So that obviously adds up though to 9 exactly. So 9 divided by 3, because there's 3 results, so you always divide, you add the results together, then you divide by the number of results, so that equals 3 exactly. Now because they've done it in decimals, I would always put 0.0, always use the same number of decimals as they have used. So there we go, there's our answer, and you need to make sure you write it into the table as well. All right, as Amy is sliding down the slide, energy is being changed from one form to another. So although this is a forces question, they have got a little energy question in there, and that's quite common to happen. And that's one of the reasons why we do these 2 topics together. Okay, so state the energy transfer occurring. So as she goes down the slide, so when she's at the top of the slide, if this is the slide, so when she's at the top of the slide, and then when she's moving down the slide, we need to think about what energies we've got going on. So at the top, she of course has gravitational, anything where anyone's ever raised up. You don't need to put potential, but you can do in brackets gravitational potential energy, and then as she moves down it, she has of course got kinetic energy. Okay, moving on to the next side. So state the equation that links speed, distance and time. Now, they don't allow just the letters S equals D divided by T. I will allow it, but in future, don't be lazy in an exam. So it should be speed equals distance divided by time. Okay, that's worth a mark. Calculate Amy's mean speed down the slide and give the correct unit. Okay, so we need to use the table to get this information. So, and the diagram, in fact. So, in fact, let's write things out properly first. So I taught you that you should always have your three S's, one under the other, put in your formula and then put in your numbers. So the distance, so let's go and look for the distance. So we highlighted that earlier, it is 5 divided by the time. And if we look at the mean time, because they've asked for the mean speed, it was 3. So you're typing into your calculator 5 divided by 3, which equals 1.7. So I'm now going to just put that over here by the units. And now I need to work out what my units are. This is really easily done by looking at the units that they've used. So meters and second. And if we remember, so I'm just going to use a pink here. So the 5 is meters. The divide means you put a per, and then the 3 is measured in seconds. So that gives us meters per second. So you get 1 mark for 1.7 and 1 mark for meters per second, but you should show your working, please. In fact, I'm going to say if you didn't write any working, I'm going to take a mark away even if you got both of these right, okay? All right then, so Matthew slides down the same slide, but he takes longer than Amy to get to the bottom. Suggest and explain why he takes longer. So they've asked you to do 2 things. They've asked you to suggest, which is to give a reason, and they've asked you to then explain why that would actually have an effect. So there are a few different options that you could go for as to suggesting a reason. So one option is that there is more friction. So maybe he's wearing sort of rougher trousers or something like that. So there is more friction. Now, I would also accept that he is heavier, weighs more, has a greater mass, because that would actually affect how fast he would go down the slide as well. But the ideal answer is that there is more friction. And why would that affect how long it takes him to go down? Well, obviously, the more friction, the slower you travel. And if you think about when we did, this was a really similar experiment to when we had the cars on the ramp and we tried different materials, like we tried bubble wrap and sandpaper and cloth, things like that. And we found that the greater the friction, the less it would travel. So it's just really a variation on that experiment. So 1 mark is for saying that there's more friction and 1 mark is for saying that more friction will slow you down. Okay? Oops. Okay, by using a motion sensor and a computer, the pupils find that Matthew's speed is constant all the way down the slide. So he's going at the same speed the whole time. Explain what this means about the forces on Matthew. Well, again, as soon as we see that word constant or steady speed, it tells us that the forces are balanced. So that's our keyword that we're going to use. This means, so explain what this means. This means the forces acting on him are balanced. Therefore, his speed remains steady. So remember, it's only if they're unbalanced where you can get a change happening. So change of direction, change of speed, starting and stopping. If there's a balance force, you can't have a change happening, remember. So 1 mark for saying that the forces are balanced, and 1 mark for explaining what that means, so that it's going to stay steady, okay? Okay, turning over to the next page where I think we've got a graph to have a look at. Alrighty, so the graph shows the motion of a model car over a period of 120 seconds. So if we look, time in seconds down here, and it's going up to 120. And then we don't have any results after that point. Write down the formula that relates speed to distance and time. We've already done this, so it's the same, S equals D divided by T. Remember, you should be writing it out in full, ideally. So we won't go over that too much. Use the graph, so use the graph, write down the distance travelled by the car in the first 100 seconds. So I'm going to go to 100 seconds, and then I'm going to go up to distance, and then I'm going to go across to distance over here, and I've got 20. And I'm going to put the units. It's quite important to put the units. So 20 meters is the distance. So you're literally just reading off the graph. All right. So calculate the speed of the car during the first 100 seconds. Give the correct unit. Really important to highlight that so you don't forget. Now this is worth 3 marks, which is where it's going to come in handy, us writing everything out properly, because one of those marks is clearly for workings, 1 is for units, and 1 is for the correct answer. So S equal, put all your S's in, S equals, S equals, S equals, one under the other. S equals D divided by T, S equals distance, 20, we just wrote that down. S divided by time, they said in the first 100 seconds, so divided by 100, 20 divided by 100 is 0.2, and then they have asked us for the units. This is measured in meters, so meters per, this is measured in seconds, meters per second. So 1 mark for this working, 1 mark for this answer, 1 mark for these units. State whether the speed of the car between points A and B is increasing, decreasing, constant, or 0. So you actually have a list of options. You need to look at the graph to do this, and it's between points A and B, and it's the speed of the car. So let's have a look at the graph here. So between A and B, you can see that the time is 100 and 120 seconds. So in this 20 seconds, if we look at the distance, it hasn't gone anywhere. The distance is 20 at A and it's 20 at B, which means that the car must have stopped. It's not going anywhere. It's not moving. So therefore, the speed, if it's not moving, well, it can't be increasing. It can't be decreasing. It can't be constant. It must be at 0. So 0 speed. It's not moving, our car. And then last question, state the total distance travelled by the car in 2 minutes. So 2 minutes is 120 seconds. So they're asking at B. Now this is a bit of a trick question because they asked us already for this distance here. Now the car hasn't gone anywhere in that last 20 seconds, so it's going to be exactly the same as it was before. It's still 20 meters. So yeah, it is a little bit of a trick question there. So add up all of your marks for this question and then fill those out onto the front of your exam. So it's out of 17. Okay, the diagram below shows a girl standing on a diving board. Don't really need to highlight anything there, I don't think. And then I'm going to just really have a look into this diagram before I go on to anything else. So we've got a pivot here. There's some support for the pivot here and the board. We've got obviously the water that she's going to jump into. Now this is the pivot line here, and on this side of the pivot we've got a distance of 1 meter. On this side we've got a distance of 3 meters, and then we've got the girl's weight is 600 newtons, or 600 newtons is her weight. So then we're going to use this and bring it forwards with us into answering these questions. So state the equation which links moment, force and distance. So if you can't remember a equation, it's always a good idea to just draw in your triangle, because it might help jog your memory. So moment equals force times distance. So this is a times, remember here. If you put m equals f times d, I will allow it, but you wouldn't normally be allowed it in an exam, okay? So don't be lazy, remember, with exam questions. All right, using the information from the diagram, calculate the moment produced by the girl. Okay, so they're asking for this moment here, okay? So the moment produced by the girl. So it says ignore the weight of the board, because of course the board would have weight too, but we're not going to bring that in because they've told us to ignore it and they haven't given us a number. So let's write out m equals. I know they don't have a line here for it, but I really would recommend doing it this way, boys. It really helps prevent mistakes. So then it's force times distance. So we're looking for our force number. Well, of course, weight is a force, so that is 600. Times by our distance, which is 3 meters. So 3 times 600 is 1,800. And they've given us the units, so I'm going to write it over here next to the units. And that's why it's only worth 2 marks, because they've already told us the units are, of course, newtons, because this is measured in newtons and this is measured in meters. It's not per, because this is a times rather than a divide, so there's no per in between. Okay? All right, moving on. The diving board is horizontal. The weight of the diver is balanced by the downward force of the support. So the downward force of this support here is balancing out our diver. Otherwise, this whole thing, if you imagine if this was the board, if there wasn't that support there holding it down to the floor, it would go like that, like a seesaw, which obviously wouldn't be great for diving. Okay, so show that the downward force produced by the support is 1,800 newtons. So they've given us the answer, and what they're asking us to do is show mathematically how we know that, basically. So they're asking us for the downward force of the support. So that means that we need F. So force equals, force equals, force equals. And this is where doing the triangle is helpful, because you can refer back to it. I'm just going to do it down here so we can see it. So if we look at F, F equals M divided by D. So M divide, oh no, my pen's running out. 1 second, guys. I'm going to have to use a different colour blue. I hope it shows up. Yes, it does. F equals M divided by D. So moment. The moment on the other side was 1,800. And they've told us that this is balanced. And if it's balanced, it means that the moment on both sides must be the same. So we can use this moment, 1,800, in here. We're going to divide it by the distance. Now, the distance, remember, on this side is 1. So divide by 1. And of course, if you divide something by 1, it's going to be the same answer as before. So 1,800 newtons is our answer. And that is the same as what they got. So we know that we must be right. Okay, moving on. So turning over to the next part of the question. This is quite a lengthy question. All right, so this part of the question is really going to test your comprehension and investigative skills or inquiry skills. So let's take some time, because it's quite meaty, quite a lot to read through. Let's take some time to read through it properly, highlight, get as much information out as we can. So some pupils decide to measure how much a metal strip bends when it is loaded. They clamp a metal strip onto a table. So they've clamped it onto a table and set up a ruler as shown in the diagram. I'm just highlighting things on the diagram to make sure I've really understood what's going on. So basically we've got a table. This is the metal rod going all the way along. So half of it's on the table, half of it is off, and it's clamped so it can't just ping upwards. We've got a ruler which only starts at the end of the table onwards, okay? So they add weights to the end of the metal strip, which bends downwards as shown by the dotted line on the diagram above. They measure the position of the end of the metal strip with no weights. Each time they add 0.5 newtons to the metal strip, they measure again. So every time they're adding a weight onto here, they're measuring oh no, sorry, the ruler's here. So as they do it, what they're doing is measuring between the point which was 0 weights and each new weight that's added. They're measuring that. It's a bit like our springs experiment that we did, but instead of a spring that's stretching, we've got a rod that's bending. The picture on the right shows the position of the metal strip against the ruler with no weights. So over here, that's it with no weights. And the position of the metal strip is measured to the lower edge of the metal strip. So they're using this lower edge here, not the top of it. Okay, so our first task is to add the ruler value to the table below for no weights added. So we're using this number here. So this is 74, this is 75. This is exactly halfway between. So this should be 74.5. And there's a leeway, you're allowed a leeway of 0.1 centimeters. So if you put 74.6 or 74.4, that would be accepted, okay? All right, so the next part of the question says, complete the table by calculating the height difference between the position. So we're calculating the height difference between the position with no weight and the positions with each additional weight. Okay, so we've got to use our calculators here, please, guys, so we don't make silly errors. And we're going to be taking this number away from, we're going to take this number away from this number every time. So it'll be this number from this number, this number from this number, and so on. Okay, so 72 from 74.5, 2.5, 74.5 minus 69.5 would be 5.0. 74.5 minus 67 would be 7.5. 74.5 minus 64.5 would be 10. And then last of all, 74.5 minus 62 would be 12.5. Okay, so it says on the grid below, plot the height difference against the weights added. And they have already done the scale for you, and they've already got the labels on the axes. So all you're having to do is plot these points on. So I'm going to use my pen just so it shows up. In fact, I might even use my pink, but you must use a pencil. If you used a pen, you would lose all of your marks in a real test. So it's worth 2 marks. So do please make sure you use pencil. Don't use dots. I really want to see crosses, please, guys, okay? So what number is it that you're actually plotting here? So it's the height difference that they've asked you to plot. So the height difference is the last column. So this is the column that you are plotting. So the first number, maybe I'll put that on that side because you can see the numbers better. So our first number is weight in newtons against height is 0. So we're going to put it at 0, 0. Then our next one is when we've got a weight of 0.5 newtons, it's stretched or bent 2.5. So it bent 2.5. I actually would recommend, because they haven't, which is very unhelpful, they haven't drawn on little lines to show where these are. So I might, before I start plotting, I think I'm going to draw all of those on. I'd really recommend that. So
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, Okay, I'm going to do the same up here. Again, I'd really recommend that you do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is very bad graphing from whoever wrote these questions.
Okay, now that I feel a bit more prepared, I'm going to go over to 0.5 and I need to go to up to 2.5. So if I go halfway, that's 3, and then I'm going to go halfway again. That's going to be my 2.5. I really think it helps writing stuff like that on again, just to check things. And if you want to be super, super considerate to yourself, then use a ruler to really check that you've got everything in line against the scale, against the axis. Okay, so there's my first point.
So my next one is at 1. So when I added 1 metre of weight, I got a stretch of 5 centimetres. So I'm going to go up from here and across from here. Now, I find it quite difficult to see, so I am just going to check with my ruler. Yep, that's the right point there. Okay, and my next one is 1.5 newtons and 7.5. So 7 would be here, so that means 7.5 would be there. Again, it's really helpful to write things on. So I'm looking at there, and is that the right place? Yep, and there. This might be one which you might want to get your parents to double check that you've plotted it accurately. You don't have to, but it might be an idea. Okay, so 2 and 10. So I'm going to follow that across. And last one, 2.5 and 12.5. Again, I'm going to use my ruler. So 12.5, remember, so don't get caught in the trap. That's 13, not 12.5. So 12.5 is, oh, can't see that, sorry guys. Let me put that away, let me bring this down. So don't get caught in the trap of thinking that that's 12.5. Remember, that's 13, that's 12.5 there. So let's follow that across. There we go. Alright, so now we have done our plotting.
So the next thing inevitably is add a line of best fit to the graph. So you can have a curved line of best fit, but in this particular instance, if we look at these, they're definitely straight. Now, the key thing is that you go to the 0. If you don't go to the 0, you won't get the mark, and then you simply just draw a straight line. Again, you should be using pencil. So you only get the mark if it goes through the 0, 0 point, and if you used a ruler, all right? So now we can go on to some graph analysis. So describe the pattern shown by the results. It's really important that you don't explain. Explain is to say why something happened. To describe is what happened. So you're literally describing this line here. Now it is actually worth 2 marks, which tells you that you need 2 different valid points that you need to make. So let's have a look at what those points might be. So I'm going to do 2 bullet points to make sure I say 2 relevant points. So as the weight is increasing, what's happening? Let's just move this. As the weight is increasing, what's happening to the height in centimeters? Well, as the weight increases, the height increases. So that's my first simple way of saying things. So as the weight increases, the height increases. So essentially what you're always doing when you describe a graph is you're always starting by linking the input variable on this axis with the dependent variable or output variable, so independent variable and dependent variable. You're just linking those 2 things together. That's what you should always be doing. And I'm linking them with saying that as this increases, this also increases. But I need to say another point. So as if I look at my line, the fact that it's straight tells me that the rate at which it's increasing is the same all the way through. It's not curved, it's not changing as it goes. So a way of saying that, which is a word we did use with springs, and this is kind of a very similar thing to the springs, is that the increase is proportional. And what that means is that it's going up the same amount each time. Now, I will allow you the mark, even if you didn't use the word proportional. If you said it's going up at the same rate, or anything that means that, then that's fine. But proportional would be an exceptional word to use. That would be the ideal word to use, guys. So try and get using those scientific words. All right. The metal strip is now removed from the table and supported at both ends. A weight of 2 newtons is hung from the centre 50 centimetre point. Now, this is quite complicated, so I might draw this out to kind of tell myself what's going on. So I might do a mini little version of it. So they've taken it off the table and they've supported it at each end like that. So here it is with supports at each end. And then they've told me that they've hung a 2 Newton weight in the centre at 50 centimetres, like that, okay? Suggest giving your reasons. So suggest and give reasons how much the centre of the metal strip is depressed by the 2 Newton weight. So they're basically asking you how much is it going to bend downwards if there's a 2 Newton weight in the centre of it. Okay, so in order to answer this, there's a bit of scientific thinking that needs to go on here. And what's crucial is that you refer back to this table. So when they added a 2 Newton weight and it was bending from one end, it bent by 10 centimetres. Now, it's reasonable to therefore consider, well, if it's got support at both ends rather than only at one end, it's not going to bend as much. So we've got a 10 centimetre bend in our previous experiment. And therefore, I'm going to divide that by 2 because I've got 2 supports. So I'm going to get a 5 centimetre depression. So let's think about how we can actually, that's kind of note taking. You don't really want that written there. Let's think about how we can explain that. So I'm going to say when there was only one support, it bent by 10 centimetres. Therefore, if there are 2 supports, it will bend. That was Doug making a funny noise. It will bend by 5 centimetres. Do you want to go outside, Doug? Sorry, guys, one sec. Let the dog out. There we go, Dougie Doug. Right, so when there was only one support, it bent by 10 centimetres. Therefore, if there were 2 supports, it will bend by 5 centimetres. Again, this will make you probably think of the springs in parallel where they only stretched half the amount because they were sharing the weight. It's a kind of similar concept to that. And I think that's the end of that question. Yes, it is. So add up all of your marks on this and then record them on here. So I got 15, well done me. All right, so let's move on then to the graph section. Question 7. An object has a mass of 2 kilograms and a base area of 4 centimetres squared. On Earth, a gravitational force of 10 newtons acts on every kilogram. Calculate the weight of the object. Give the correct unit. All right, so they've told us that it is 2 kilograms and that 10 newtons will act on every kilogram. So we literally just times it by 10. If you remember, this is how we worked out our weights. We times them by 10. So it's literally 2 times 10, which is of course 20, and it's weight, and weight is measured in newtons because all forces are measured in newtons, and that's worth 2 marks, 1 for this part and 1 for this part. Okay, give the equation which relates pressure, force and area. So again, I'll allow you to be lazy and do P equals F divided by A, but ideally you would write it out properly. Pressure equals force divided by area. And if you couldn't remember it, it always helps to draw in your triangle first, and therefore you won't make silly mistakes. Okay. The object is placed on a flat surface. Show that it exerts a pressure of 5 newtons per centimetre squared. So they're giving you the answer, you just have to show the maths. So it's pressure, which is P equals force divided by area. Force, well, the force is 20 newtons. We worked that out earlier. Divided by the area. They told us the area earlier in the question was 4 centimetres. It's got a base of 4 centimetres squared. So there's our area. 20 divided by 4 is, of course, 5. And they already told us the units, but it doesn't hurt to put them in. 5 newtons per centimetre squared, which is what they get. So we know that we're right. Give ourselves the marks. All right. If you were to take the object to the moon and place it on a flat surface, some values would be different. We did this in class, so you should know this. Write larger, smaller, or the same beside each quantity below to show how its value on the moon compares with on Earth. So, if we remember, the moon is about 1/6 the size in terms of mass of the Earth, so therefore the gravity on the moon is about 1/6 the gravity on the Earth. So the force it exerts on the flat surface, so will the downwards force, the weight, so this is weight essentially, the force it exerts on the flat surface, they're actually asking you the weight, so will the weight be the same or different? Well, if you think about it, if it's 2 kilograms on Earth, we timesed it by 10, 2 kilograms times 10, and that gave us that it was 20 newtons. We wouldn't be timesing it by 10 if it was on the moon. We'd only be timesing, well, in fact, we'd be dividing this by 6 to get the weight on the moon. So no, it wouldn't. It would be smaller because we'd be dividing by 6 because the gravity is only 1/6 of the gravity on the Earth. Okay, the area in contact with the flat surface. Well, the area of our block isn't going to change in any way. That's going to be the same. Area is not affected by gravity. And then the pressure exerts on the flat surface. Well, if we think, instead of having P equals 20 divided by 4, we'd have a much smaller number here. So, in fact, let's work it out for the sake of being correct. So 20 divided by 6. So we said 20 divided by 6 up here. That's 3.3 reoccurring. So it's only 3.3 reoccurring newtons. So that's our new, and then we divide that by 4. So the pressure, so 3.3 divided by 4 is going to be 0 point something, isn't it? So that means the pressure is going to be way smaller than it was up here because this number's way smaller. So our pressure is going to be smaller, okay? So smaller, the same, smaller. The object is lifted and held at rest a few centimetres above the flat surface. What form of energy has it gained? So again, this is a forces question, but it's linking back to energy. And once again, it's gravitational. We've had a lot of gravitational ones, haven't we, today? Gravitational energy. Will this gain of energy be less, more, or the same if the experiment is repeated on Earth? So, remember that there's more gravity on Earth, so therefore there's going to be more gravitational energy if you lift it up the same amount on Earth because the gravity is bigger. So that should be more. And that is the end of that question. So if you add up all of your marks and write them onto the front. So it's out of 10. So this should look very familiar because we did this exact experiment. Sarah is investigating how much a spring stretches. She hangs different masses from it. Suggest one safety precaution which Sarah might take when carrying out this experiment, and explain what could happen if she did not take this precaution. Well, if you remember, boys, what we did is we wore goggles because if you remember, I told you, and in fact it did happen with a few people's, the springs actually snapped when we stretched them too much. So it's really important that we wear goggles, because if the spring can snap and hit your eyes, which would obviously be really dangerous. Now there's another option actually, because if you think we did counterbalance this and make sure our feet weren't underneath, anything that where we're talking about the fact that it can fall on you and hurt you. So if you said anything up here about making sure it doesn't fall on you, so not putting your feet underneath or counterbalancing it, and then explained that it can fall on you and hurt your feet, that's also totally acceptable as well. All right, name the upward and downward forces which are acting on the set of masses. So I would probably draw this onto the diagram. I always think it's a good idea to draw onto diagrams. So what's pulling it down is, of course, always weight. I think they'll probably allow gravity, but weight is the name of the force, remember. And then what is in the upwards direction? Well, one that we haven't mentioned yet, actually, it's tension. It's the tension of the spring. So weight and tension, or tension and weight would be more sensible to say, wouldn't it, Mrs. Lally? Okay, there we go, tension and weight. All right, nearly there, guys. So Sarah writes her set of results in a table which shows the extension of the spring. Dougie, don't be barking at people. As the mass hanging from it is increased. Okay, so here's the mass and here's the extension of the spring, and you have to draw it into a graph. And this time they have labelled the axes for you, but they haven't written the scales on. So the mass goes up in 100 and it needs to go up to 500. So it's a really nice, easy one of 100, 200, 300, 400, 500, there we go. And then the extension, that one needs to go up to 10, I would say. So let's look at what times table would work. Remember, it's really important that you don't put these numbers up the side. These are not a scale. These are not a times table. So let's think about the 2 times table. 2, 4, 6, 8, 10 works perfectly. 2, 4, 6, 8, 10. There we go. Now we're ready to plot.
So now you have to keep clicking back and forth, sorry about that. So 102. Remember, you used to be using pencil, but I'm using pen, so it shows up. 203.7. So here it will really help you if you show where 3 is, and then 2, 4, 6, 7 is there, and then 200 is here. So again, you can then do that thing where you check that you've definitely got it right. Yes, that's right. Yes, that's right. So if you're marking this yourself, do use a ruler to check, and use it in your class to check as well. All right. So 300 is 5.7. So I'm going to put that there, and then 5 is here. 5.7 is therefore here. Oops. Gosh, this does my eyes in. There we go. 5.7 and 406.5. So 6 is here, which means that 7 is here, which means that 6.5 is there. And last of all, 9.4. So we don't need a ruler actually there. So 9 is here, 2, 4 is here. So it's 3 from the bottom there. There we go.
And there's our graph. So marks wise, add sensible scales. So you need 100 times table here, 2 times table there. Plot the data. So you lose a mark for each one you did incorrectly. Label with a P the point which does not fit the pattern of the others. So it should quite obviously be this one here, because if you look, these are making a nice straight line. That one looks below where it should be. And then it says draw a line of best fit. So you don't include anomalous results or incorrect results when you're drawing a line of best fit, because they obviously aren't right. So I'm going to draw my line like that. So you can see I'm hitting 2 points. This one's slightly above, this one's slightly above, okay? And that one is nowhere near. All right, so Sarah is surprised that one of the points does not fit the pattern of the others. Suggest a possible reason for this. So this happened to us quite a lot when we were doing this because it was quite difficult to measure. I would put, don't just put human error, you need to explain it, but you can put human error and explain. Dougie! So that they may have read the ruler wrong, or they may have measured wrong, that would be fine, or that they may have just written it down wrong, that would also be fine to write. Written down wrong. Anything about measuring it incorrectly, basically. Okay. Name a piece of laboratory apparatus which uses the extension of a spring to measure a particular quantity. Well, that is a force meter or a Newton meter. We used those in class multiple times. Either name is fine. And then last couple of questions. How could they make their experiment more reliable? So she did have a wrong result, so it's obviously not reliable. So 2 marks here, and that's because 1 mark for saying that you repeat it or that you do it 3 times, and 1 mark for saying that you then calculate an average. So you can't get 2 marks unless you said to calculate an average as well. And the very last question of the test, what should they keep the same to make their experiment fair? So things that they should keep the same are they should use the same spring each time. It wouldn't be any good if you used a different spring. So the other thing that they need to do is use the same weight of mass. So they can't, for instance, use 100 grams and then a 50 grams and then a, you don't really get 90 grams, but you know what I mean. So it needs to be the same mass each time. You mustn't include here things like rulers, because all rulers should be the same because they're pieces of measuring equipment, okay? So that means that you have finished marking your test. So add up all of these last question marks and write them onto here. Then you can add up all of these and that will give you your percentage. Now, I obviously can't tell you what's a good percentage at the moment because I don't know how you've all done. But once I get all of your results in, then I will let you know what the average was for the year group and so on. So what I would like you to do is to go onto Shobi and upload this front page. If you're worried about other people seeing what your marks are, then you can ask your parents to email this to me and that way nobody else will be able to see. But if you've done really well and you're not bothered, then you can just upload it to Shobi. And then once I've got everyone's results back, we'll have a look through at how to kind of look at where you went wrong, how to improve and that kind of stuff. Okay? And well done, because I know this isn't the funnest thing ever, guys. So just to be clear, if you're uploading it to Shobi, please go to week 1 in year 7 and then upload it to the test score activity. Okay, thanks.